Let us discuss indirect spin and spin interaction in proton NMR. In NMR spectroscopy, indirect spin-spin coupling, what we call this as J coupling, refers to magnetic interactions between nuclear spins transmitted through bonding electrons. Indirect spin-spin coupling or J coupling is a magnetic interaction between two nuclear spins that occurs through the bonding electrons connecting the nuclei. Spin-spin coupling occurs between neighboring NMR active nuclei and causes splitting of NMR spectra. J coupling is an indirect interaction between two nuclear spins that arises from hyperfine interaction between the nuclei and the local electrons. It contains information about relative bond distances and angles. Most importantly, it provides information on the connectivity of chemical bonds. In NMR spectroscopy, indirect spin-spin coupling, otherwise what we call this as J coupling, refers to magnetic interactions between nuclear spins transmitted through bonding electrons. It provides the information about molecular structure and connectivity. J coupling, also known as scalar coupling, is an indirect interaction between two nuclear spins that arises from hyperfine interactions between the nuclei and the local electrons. It works out with the interaction mediated by the bonding electrons, not directly through the space. Indirect spin-spin coupling or indirect dipole-dipole interaction or J coupling is known as a magnetic interaction between individual nuclear spins transmitted by the bonding electrons through which the nuclear spins are indirectly connected, chemically and magnetically equivalent nuclei. Spin-spin coupling refers the interaction between the magnetic fields of neighboring non-equivalent nuclei leading to the splitting of NMR signals. Significance in NMR. J coupling is a key parameter in NMR spectroscopy, providing valuable information about 1. Atomic connectivity. It reveals which atoms are directly bonded to each other. Molecular structure. It helps to determine bond distances, angles, and the relative proximity of interacting nuclei. Splitting of NMR signals. J coupling is responsible for the splitting of resonant lines in NMR spectra, leading to multiplets, doublets, triplets, quadrets, and so on. The n+1 rule. The number of peaks in the multiplet is determined by n+1 rule, where n is the number of neighboring protons. Examples: a proton with one neighboring proton will split into doublet, n equals 1. So use n+1 rule. So 1 + 1 that will give us 2 peaks. A proton with two neighboring protons will split into triplet. So n equals 2 implies 2 + 1, which is equal to 3 peaks. A proton with three neighboring protons will split into quadret, that is when n equals 3, which will give us 3 + 1, which is equal to 4 peaks. Thus, spin-spin coupling refers the interaction between magnetic nuclei in molecules leading to a fine structure in NMR spectra known as scalar coupling or J coupling. It results in the splitting of resonant lines and is caused by interactions between nuclei via the electrons in chemical bonds. The main application is that the spin-spin coupling and the splitting patterns are important tools for determining the structure and connectivity of molecules in NMR spectroscopy. Detailed explanation. When the NMR spectrum of hydrogen molecule was recorded under very high resolution, The spectrum observed showed more lines than that expected under chemical shift consideration. So far, we have neglected the effects of the indirect interaction between magnetic nuclei within the molecules. In the case of H2 molecules, that is deuterated hydrogen gas, which consists of two hydrogen atoms, one bonded to a deuterium atom and another one is proton, spectrum would show a triplet. This is because the two hydrogen atoms are in different chemical environments due to the presence of deuterium, resulting in three distinct signals. The additional splittings observed in H2 molecule are due to this indirect interaction between protons within the molecule. In the proton NMR spectrum of the H2 molecule, the proton signal splits into a 1:1:1 triplet due to heteronuclear coupling with a deuterium nucleus with a peak-to-peak separation smaller than the J, which is function of D, H coupling constant. The distance between the peaks in the triplet is related to the coupling constant, which is nothing but J. It depends on D, H, which is a measure of strength of the interaction between the two nuclei. The proton NMR spectrum of H2 molecule shows a triplet pattern, that is three peaks, instead of a single peak. This is because the deuterium nucleus 2H has a spin of 1 and it can exist in two possible orientations, spin up and spin down, relative to the proton. These two orientations create two different magnetic environments for the proton, resulting in the splitting of the proton signal into a triplet. The peak-to-peak separation between H2 multiplex peaks, that is J effective, is smaller than the J depends on D, H coupling constant. Nuclear relaxation and the intermolecular interactions can have an influence on J effective. J effective determined from the proton NMR spectrum is smaller than from deuterium NMR spectrum. For our discussion, first let us consider the simple H2 molecule. Since the magnetic moment of proton and deuteron are different, they show resonance at different magnetic fields. The spin of proton is half and that of deuteron is 1. The system has two electrons. The proton's spin interacts with the spin of electron 1 and as a consequence, their spins will be antiparallel. This electron in turn interacts with the electron 2, forcing its spins to be antiparallel with its spin. Electron 2 in turn interacts with the deuteron nucleus and as a consequence, their spins will be antiparallel. In other words, as a result of the interaction via electron cloud, if the spin of proton is up, the spin of the deuteron would be down. This indirect interaction between two nuclei via the electron cloud is termed as the indirect spin-spin interaction or electron-coupled spin-spin interaction. When the proton spin interacts with the deuteron spin, it sees the three different orientations of the deuteron spin. That is, when I equals 1, we have the formula 2a plus 1, which is equal to 3. Hence, the spectrum of proton splits into three components of equal intensity. In the same way, the deuteron spin sees the two orientations of the proton spin via the electron cloud in the molecules, splitting deuteron spectrum into two. So this is exactly as shown in the figure. So this is what the spin-spin interaction in H2 molecule takes place. Unlike the chemical shift, which is directly proportional to the magnetic field, the typical J values in some of the molecules, some of the general conclusions with regard to spin-spin interactions are: 1. Spin-spin interaction is independent of the strength of the applied field B0. Equivalent nuclei do not interact with each other Multiplicity is determined by the number of neighboring groups of equivalent nuclei for protons. If n is the number of equivalent nuclei in the neighboring group, the expected multiplicity is n plus 1. When the chemical shift del nu very larger than that of J, coupling constant. The intensities of multiples are symmetric with relative intensities given by the coefficients of the terms in the expansion of A plus B. Coupling constants are dependent on the number of bonds between the interacting nuclei. Coupling is almost negligible at distances greater than 3 bonds. If 3 is charge delocalization, as in aromatic system, interaction beyond 3 bonds is possible. Thus, the spin-spin coupling means that an absorbing peak is split by more than one neighbor proton. Splitting signals are separated to splitting constant J H, where is called the coupling constant. The splitting is a very essential part to obtain exact information about the number of neighboring protons. The maximum of distance for splitting is 3 bonds. Chemical equivalent protons do not result in spin-spin splitting. When a proton splits, the proton's chemical shift is determined at the center of the splitting lines.